Today, we're going to cover introduce material for exam 6. Since there's nobody here in person to take the paper exam, I'm going to go ahead with the exam. Chapter 15, exam 6. We just covered chemical quantities, which is essentially a discussion of stoichiometry. And that is, if you know how much reactants going in, you can predict how much reactants coming out, products are coming out. Now, solutions, we're going to narrow our focus. And this is an extension of stoichiometry. We're going to look at solutions, how to deal with solutions, which you recall is a homogeneous mixture. And reactions, many reactions occur in solution. So here's an outline. We're going to talk about things such as solubility, how to quantify a solution, how to identify the amounts of the components in a solution relative to one another. And then we're going to discuss the stoichiometry of those solutions and how to deal with those types of problems. All right. There are only 3 documents that are in the handouts for today: the PowerPoint slide set, the review problems, and the worked problems. The key for the review problems, of course, is in Brightspace, but I don't print that one out. So if you were here in person, you'd get those 3 copies, hard copies already printed out, handed to you. Okay, what is a solution? We learned early on in the semester that a solution is another name for homogeneous mixture. That is, no matter where you look in the mixture, the relative amounts of all the components are exactly the same. But we're going to further that understanding by adding some definitions. So, when we talk about a solution, there are various components. The major component in that mixture is called the solvent. And for our purposes, not all the time, but most of the time, the solvent is going to be water. And when we designate that component in a reaction, we use this abbreviation, AQ for aqueous. Okay. Everything else, you can only have one solvent. One solvent. You can have many of the minor components called solutes. Okay. And they can be anything. Anything that will actually go into solution and produce a homogeneous mixture. The aqueous solution I've already mentioned, and that's what the AQ stands for. It stands for aqueous. And that always means that the solvent is water. Now, it doesn't have to be water. The solvent doesn't have to be water. It can be almost anything. In fact, it can be any phase that we studied, gas, liquid, or solid. So here are examples of different types of solutions. The first one is where all of the components in the solution start out as gases. The air we breathe is a solution of 79% nitrogen and 21% oxygen. Now that adds up to 100%, but there are more minor components. So in this case, the major component, the solvent, would be nitrogen. And the largest solute concentration is oxygen. And then you have other things like water vapor, carbon dioxide, other, actually xenon this is, you know what? I don't think it's 79. I believe it's 78. 78%, because it's 1% argon. Yes, 78%, 21%, and 1%. And then minor components, much less than 1%, make up the difference. So that's a solution of a gas in a gas. Other types of solutions that we're more familiar with are alcoholic beverages. Right? Water is the solvent, and ethanol, or what we'd normally call alcohol, the drinking kind of alcohol, is a solute. And depending on the type of liquor, you have other components. But that's a liquid in a liquid, homogeneous mixture, solution. You can actually have a solid in a solid as a solution. And a brass is an example. Brass is a solution of copper and zinc. Since I don't recall the percentage mixture, I can't tell you which one is the solvent and which one's the solute. I think copper is the solvent. Zinc would be the solute. Oh, no, I'm sorry. Copper, that's bronze. Copper and zinc is bronze. Copper and nickel is brass. Okay. So I'm pretty sure that nickel is the solute in this case. But you can't just take a block of copper and a block of nickel and push them together and make a solution. Right? They won't mix. You have to melt them. You have to make them into liquids. Then you can mix them. And when they solidify, you have a solid solution of brass. You can have gases in the gases dissolved in water, or gas dissolved in a liquid. And our example is carbonated beverage or soda, which is carbon dioxide dissolved in water. That's why it fizzes, why it bubbles. And then the more commonly understood solutions are those where a solid is dissolved in a liquid. Seawater is a good example, right? The major solid component, a formerly solid component in seawater, is sodium chloride, or table salt. But there are other ions dissolved in seawater. In fact, there are gases dissolved in seawater. Right? Carbon dioxide is dissolved in seawater. Oxygen is dissolved. So you can have multiple types of mixtures where you can have gases, solids, and liquids, all three solutes dissolved in the liquid. Okay. So here we have sodium chloride dissolved in water, and you start out with a solid plus a liquid, and you get a liquid. And by the way, when sodium chloride goes into solution, right, it may start out as a solid, but when it goes into solution, in aqueous solution, it actually breaks up into its component ions. That's what the illustration is showing you. You have sodium ions and chloride ions are actually in solution. not the sodium chloride molecule, so to speak, not that formula. And this is true for any ionic substance. If the ionic substance goes into solution, it breaks up into its individual ions. There are ionic substances that will not dissolve to a significant degree in make a solution. And we typically discuss those in terms of solubility in water. We'll mention those again in a few minutes. In fact, we're going to talk about them right now. So when we're trying to determine the solubility of an ionic substance in water, or actually in any solvent, the solubility of an ionic substance is improved based upon the polarity, which is a physical identity of the solvent. So if the solvent is polar, that is like water, right, with its hydrogens bound to it, and the individual bonds are polar toward this negative, right? So that leaves this one slightly positive and this one slightly positive. That's what that little delta means. Not a full charge, just slightly positive. And that makes the oxygen slightly negative. Then overall, the molecule is polar negative toward the oxygen. What that means is when you put the ionic substance in the solvent, water in this case, what happens is you have this crystal lattice of positives and negatives. What happens is, if this is the outside of the crystal, the water molecule approaches like that with this negative side and that positive ion, and they form a Coulombic attraction, right? Just like opposite charges attract one another. And then this end becomes attracted to other water molecules. Right? And they apply a force. They pull on each other with enough force that they can supply the energy required to remove that sodium from the crystal. And we can argue the same scenario for chlorine, only now the hydrogen approaches the chlorine, positive side approaches the negative chlorine. And that's called a process of hydration. And once this sodium ion gets free, then it's surrounded by water molecules. Well, the solubility of sodium chloride is enhanced based upon the polarity of the solvent. So polar solvents are more likely to dissolve, bring into solution, ionic compounds and polar compounds. Right? So if we have a polar compound like ethanol, like that, that's the drinking kind of alcohol. Then you have this is slightly positive, this is slightly negative, and the water then will associate itself, that positive here, and this negative, this positive will be associated with this negative side. Okay, so that brings the ethanol into solution more efficiently. We can make the same argument with table sugar. Oh, we simplify it. Let's talk about glucose. Table sugar is glucose and fructose together. It's easier to talk about it in terms of glucose. All right. So that's glucose. And notice it has all these alcoholic groups, just like the ethanol around it. And these associate with the water molecules, just like we described earlier. And that brings the glucose into solution. Does the same thing for table sugar. Right? It has all these hydroxyls around it, and that amplifies the attraction for the solvent and brings it into solution. So and there's an illustration of what happens to a sodium chloride crystal when the waters start to hydrate the ions. And there's your example for ethanol and its association with the water molecule. Okay. Oh, good. So there's the structure of sucrose, which is a disaccharide. It has glucose here, and it has fructose. Glucose is over here on the left-hand side. Fructose is on the right-hand side, and they're bound together covalently through this linkage. And they've got all these hydroxyl groups scattered around them, and that offers opportunity for water to associate to form a type of bond. It's not a covalent bond. It's not an ionic bond. It's an intermolecular attraction. And the more of those you have, the more opportunity water molecules have associated with those various points and hydrating the molecule, bringing it into solution. Right? Now, just the opposite happens if you have a polar solvent and a non-polar, actually, it's non-polar, but it's not going to give you a homogeneous mixture because oil has no polarity to it. It's a non-polar molecule. So non-polars are not attracted into polar solvents. And that's why they form two layers based solely on their densities. So we can tell from this example that oil is less dense than water because it floats on top. But they don't mix, right? You don't form a solution. So what we develop is a rule of thumb. And the rule of thumb is like dissolves like. What we mean is polar solvents dissolve polar solutes, and non-polar solvents dissolve non-polar solutes. Now, when we can, we have a conceptualize the solvation process. All right, so when you have the, the water here, and you want to put something into it that is, say, well, let's keep it simple, sodium chloride. Okay. One of the things you have to do is make room for the sodium and the chloride ions. And we call that make a hole. Right? So first thing you do is make a hole. And that requires an input of energy because these water molecules are attracted to one another, right? Through those intermolecular forces of slightly opposite charges. So you got to get those apart to make a place for sodium and chloride. You have to add energy into it. So we add energy. This is endothermic. We have to add energy to get that hole open. And then you have to add energy to, you have to break bonds holding the sodium and chloride together. And that's another endothermic process. Right? You have to pull those things apart, and you have to pull these apart. This is our concept. So this is like step one. This is step two. Then when they come together, they form those intermolecular attractions, and you get the, just call it the attraction. The attraction of ions with water. And this is exothermic. That is, you get some energy back. Okay? So we put energy in. We put energy in here, we put energy in here to break those bonds. Then we form new bonds between the water molecules and the ions, and you get some energy back. So when you add up how much energy you put in here and here against how much energy you get back, the difference tells you whether or not the solution is going to get cold or get hot. If you get a lot of energy back, then it's going to get hot. If you don't get much energy back to balance what you put in, then the solution is going to get cold. All right. Which of the following solutes will generally not dissolve in the specified solvent? Okay. So let's look at A. A through D. We want to mix carbon tetrachloride in water. So this would be the solute here, and this would be the solvent. All right, so we want to put carbon tetrachloride in water. Well, you have to know something about your compounds, right? Is carbon tetrachloride polar or nonpolar? Right? Because the solvent is polar. Carbon tetrachloride is nonpolar. So the question is, does the solution form? Solution? No, you won't get a solution. Will not dissolve. Now, in order to understand how carbon tetrachloride is nonpolar, you have to know something about its structure, right? And we haven't gone into that much detail, so you have to be told. How about ammonia? Ammonia is polar. So will it dissolve in water? Yes, it will dissolve in water. Methanol, CH3OH, right? This is commonly called wood alcohol. This is the kind you don't drink, right? Unless you want to go blind. And then mix that in water. Well, you see the alcohol groups here are just like the ethanol that we discussed earlier. So this one is also polar, and it will dissolve in water. Okay. And how about nitrogen gas and methane, methane. CH4 or methane, right? Methane is nonpolar. Nitrogen is nonpolar. So we should, yes, we should get a mixture there, a solution. Now the question is, which of the following generally not dissolve? So the first one is the only one that satisfies that condition. Rest of them will make solutions. All right. The solubility of any solute. Once we've established that it is soluble, here, any example where the solute is soluble in the solvent, then we have to recognize that there are limits. Right? The solvent will only hold so much of the solute. One exception to that is gases. Gases are infinitely miscible. That means that there is no limit to their solubility. And that's largely because gas molecules are so far apart and they don't interact as strongly as liquids and solids. And there's so much room in there and there's little interaction, then you can put any gas in that you want to. So gases always form solutions. And they have no limits to their solubility of a gas in a gas. Now, when you dissolve, say, a liquid in a gas, or the other way around, there are limits. There's still limits. So it's only gases and gases that have unlimited solubility. Everybody else, all other possibilities have limits to their solubility. When they have reached that limit, the maximum amount of solute dissolved in a solvent, we say it's saturated. And this is dependent on several things. Is it a solid dissolved in a liquid? That's dependent on temperature. Is it a gas dissolved in a liquid? Well, it's dependent on temperature too, but it's a different dependence. So let's confine our discussion to solids and liquids. It's a little easier to understand. Saturated solution will be the maximum amount of solute that will dissolve in a solvent. Now, how do you know when you have, at a given temperature, you have a saturated solution? Well, if you're dissolving a solid in a liquid, and there's your solid, and here's your liquid, plus solute. Some of this solid actually goes into solution, and we know that it's saturated when there is solid on the bottom of the container. This will not go into solution. That means there's no more room. That we can tell is a saturated solution. Anything less than saturation is called unsaturated solution. Now, many situations will produce what we call supersaturated solution. That is, there's no solid on the bottom here, but there's more solute than can dissolve at a given temperature. Okay. One characteristic of these, well, the first characteristic is there's more solute in this solution than there should be at that temperature. The other characteristic is that these types of solutions are extremely unstable. The slightest disturbance will cause the excess amount of solute to drop out of solution and settle on the bottom of your beaker. the way you produce a supersaturated solution is you heat up the solvent and then you add more solute in it, enough solute to dissolve at that temperature, but more solute than would be allowed at a lower temperature. Then you set the beaker aside and let it cool slowly. And you can cover it and do not disturb and let it cool. And very often what you'll end up with is a supersaturated solution. Now, all you have to do is sometimes just shake the beaker or put a glass rod and stir it, or take your spatula and just scratch the inside of the beaker, and the excess solid will drop out of solution. Oh, I left one out. Take a crystal, a pure crystal of the solute, and drop it in the mixture. That provides a site of nucleation, we call it, where the ions from the dissolved solid can associate with that crystal, and they will aggregate to the crystal, and the crystal will grow in size until you reach a normally saturated solution at that temperature. Okay. Now, because solutions are mixtures, the amount up to the saturation point, the amount of solute in the mixture can vary, because we're not changing the identity of the solute or the solvent. They're retaining their identities, and they can be separated by physical means. And they can, the solute can be percentage-wise different amounts in the solution. And we need ways to quantify that. So that's where we're headed next. We want, in effect, to specify how much solution is in a given amount of solvent. Now, you can identify this qualitatively, right? Before we get to the quantitative measures, you can say qualitatively, either the solution is concentrated, that is a relatively large amount of solute dissolved in the solvent, up to and including saturation. But you're close to saturation when you describe a concentrated solution. Or it can be a dilute solution, that is, very small amount of solute in the solvent. Now we're going to talk about, that was qualitative description of concentration. Now we're going to quantify it. We're going to use quantitative measures of and expressions of solution concentrations. And the first one we talk about is mass percent. And all we have to say is, what's the mass of the solute? You can use any units of measure you want, divided by the mass of the solution. Times 100. And that'll give you percent. Now, one stipulation is the units of mass for the solute must be exactly the same as the units of mass for the solution. And the mass of the solution is, of course, the summation of the mass of the solute plus mass of the solvent. Okay, that's what this is equal to. Now, the nice thing about this expression is it's very convenient. And it does not respond, it does not change with temperature. Right? If you increase the temperature or decrease the temperature, this value remains constant. Once you've established that concentration of a solution, you can heat it up, you can cool it down. The mass percent will still be the same because mass does not change with temperature. So what's the mass percent of a glucose solution when we have 5.5 grams of glucose? Like 5.5 grams of glucose and 78.2 grams of water. Now, what's missing here? It's the mass of the solution, right? Glucose is part of the solution. So you have to add that many grams to that many grams of water to get the grams of the solution times 100. And you do your calculation, and you should end up with 6.6%. Okay? That's the mass percent calculated for this problem. Now, another way to quantitatively express concentration for a solution is molarity. Molarity has several advantages over mass percent. One of the advantages is once you determine the molarity, you're talking about numbers of molecules per liter of solution. And once you've determined the number of molecules, the mass of the compound or the element doesn't matter. You've determined the concentration based on numbers of particles, numbers of molecules. So for that reason, this calculation is moles of solute per liter of solution. Okay, that's the definition of molarity. Now, if you have mass percent, you know the mass of the solute. As long as you know the formula for the solute and the formula for the solvent, then you can make a conversion from this one to that one. But you've got to be able to convert mass into moles in order to do that. All right, so if we know how many moles of the solute we have, and we know that the total volume of the solution is 1 liter, then we have a value of molarity. Let's see, we got a problem. Hey, there's the expression. So if we have 6 moles of hydrogen chloride dissolved in 2 liters of solution, then we have a 3 molar HCl solution. Now, if we take out a fraction, a small amount of that solution, say we take out, instead of 2 liters of solution, we take out half of it. So if we take 1 liter of solution and put it in a separate beaker, how many moles of hydrogen chloride will we have? We took out half of the solution. Now we only have half of the moles. So now we only have 3 moles of HCl. That's another advantage of this expression of concentration. Right? We can take out small amounts of the solution once we know its concentration. And then we also know how much solute is in our possession then. These expressions of concentration are intensive properties. I know we've discussed that before. Remember, intensive properties do not depend on the total amount of the substance. So if we have 2 liters, excuse me. Yeah. If we have 2 liters this, we know we have 6 moles. If we have a half liter, we know we have 1.5 moles. But the concentration is always 3 molar, no matter how much we possess. That's an intensive property. So let's take an example. Another example. Say we have 1 mole of sugar, and I assume they mean sucrose. So if we have 1 mole of sucrose, and we dissolve it in enough water to make 125 milliliters of solution, what's the concentration in molarity? Well, this is the right unit here, moles, but 125 milliliters is not liters. So we need to convert 125 milliliters, right, equals, excuse me, how many liters? Well, we can do it this way with a conversion factor, right? We know how to do that. Milliliters per liter, cancel the milliliters. How many milliliters in a liter? 1,000, right? So we divide this by 1,000, and we get 0.1250 liters. That's what we put here. Okay. Let's see, let me preserve my significant figures here. There we go. So our answer can have 3 significant figures in it because this is a divide situation. Divide 0.125 into 1 is what? Well, I'm gonna let the slide tell us what it is. Eight molar. So this solution that we just made is 8 molar concentration of sucrose in water. Well, it doesn't say water, but I'm assuming. All right. We got another example here. Calculate molarity for this situation. Right, in this case, we have 500 grams of potassium phosphate. Now, this is one of those word problems where you have to have obtained and practiced the skill of converting mass into moles. And you also have to know how to write the compound, potassium phosphate. Right? This is a polyatomic ion with a 3- charge. Potassium has a 1+ charge. That means we need 3. Okay, so there's our compound, potassium phosphate. If you cannot do that, then this problem is unsolvable because you need to know the molar mass of that compound in order to convert the 500 gram mass into moles. If you can't do that, then you cannot solve the problem. So what's the molar mass of potassium phosphate? Well, we have to go to our periodic table. And potassium is 39.10. So we have 3 times 39.10 for potassium. Then phosphorus is 30.97, and this is grams per mole. right? That's molar mass. And then we have 4 oxygens, and each one of those is 16. And we add those together. And that will give us the molar mass of potassium phosphate. And I get 212.27 grams per mole. Now we can convert 500 grams of potassium phosphate into moles. Which is 2.355 moles. Now we can apply this equation because we already have the volume of the solution given to us, right? So the molarity of this solution is equal to 2.355 moles of potassium phosphate per 1.50 liters. And that's 1.57 molar. All right. I think I've got it animated here. There we go. 1.57 molar. So we're using skills that you should have learned early in the course. And if you don't feel comfortable with those skills, that's something you need to spend considerable amount of time on to master them. All right. Now we're going to use this molarity formula to answer a different question. Right? If we say that molarity is equal to moles, and that's my abbreviation for moles, that little n is moles, divided by volume. Right? We know this is moles and this is liters. But this is a formula. It's a mathematical expression. And if we know the molarity and we know the volume, we can calculate the moles. Or if we know the moles we want and we know the molarity, we can calculate the volume that we need. So right, in this case, we know that the concentration of sucrose is 10 molar. Okay? And we know that we need 2 moles of sugar. And our unknown is volume. So if we solve for volume, we put the volume over here and put the molarity over here, volume equals 2 moles divided by 10 molar. Or molarity, remember, is moles per liter. Moles per liter, right? Numerator, denominator cancels. Liters is in the denominator of the denominator, which makes it the numerator. So the liters comes up here, and we have 2 divided by 10, which is 1 divided by 5, or 0.200 liters. That's the volume we need from this solution to give us 2 moles of sugar in our possession. All right. Most glassware is not calibrated in liters. It's calibrated in milliliters. So how many milliliters do you have here? That's how many milliliters. Right? You should be able to do that also. All right. So let's make room. Let me see how much time I've got. But got about an hour left. Okay. Let's see, we have 54 slides. 54 slides, and I'm on before. Okay. I was checking how many slides I have to go. I'll probably, there's a good chance I'm not going to finish the lecture today, so I'll continue at our next meeting, which is on Thursday, which is fine because Thursday's a buffer day. All right. So say we have two separate solutions we want to make. One solution has sodium hydroxide in it. The other solution is made from potassium chloride, and they're each dissolved in separate containers, separate solutions, 250 milliliters each. All right. And we have 100 grams of each of the compounds. What's the molarity of each one? Okay. So for the sodium hydroxide and potassium chloride, we have 100 grams each. How many moles of each one do we have? We know we're going to need that. So what we need is the molar mass of sodium hydroxide. Right? So that's sodium is 23, oxygen is 16, and hydrogen is 1.01. That's 7, 40, 40.01. Okay. Now we need the molar mass of potassium chloride. Potassium is 39.10 grams per mole, right? These are molar masses. And chlorine is 35.45. It's 5, 5, 14, 74. So this would be 74.55 grams per mole. So we'll calculate the moles of each one we have. And you can see right off that we're going to have fewer moles of potassium chloride than we do of sodium hydroxide. And this is 2.499 moles. And this one is 1.341 moles. Now we can calculate the concentrations. Right? The molarity of sodium hydroxide is equal to 2.499 moles per how many liters? We got milliliters again. How many liters is that? 0.2500 liters. How about this one? Molarity of potassium chloride is equal to this many moles divided by 0.25 liters. Okay. So let's see, I'm going to do this one first, which is 5.37 molar. And this one is actually 10.0 molar. All right. So there's the animated version. For sodium hydroxide, we got 10 molar. Potassium chloride, we have 5.37 molar. So notice that we have equal masses of each of the solutes, but we don't have equal molarities, equal concentrations in molarity. All right. That's the lesson of that story. All right, let's make room. Talk about the next one. Maybe I should identify this one as part 1, just in case I don't finish the lecture. All right, you have two hydrochloric acid solutions, labeled solution A and B. Solution A has a greater concentration than solution B. Which of the following statements is true? Well, let's put what we know up here, right? Solution A and solution B. Right? They're both hydrogen chloride. Let's say it's hydrochloric acid. Right? We know that's true. Need a new marker. We also know that solution A has a greater concentration than solution B. Let's see what our choices are. All right, it looks like we're dealing with molarity here. So the molarity of A is greater than the molarity of B. Right? We're given that. Right. So which of the following statements are true, is or are true? Well, let's see. What do we have to deal with? A. If you have equal volumes of both solutions, solution B must contain more moles of HCl. If you have equal volumes, what does molarity mean? Molarity of A equals moles of A per liter, which is greater than molarity of B, which is equal to moles of B per liter. All right. So if we have equal volumes, we have equal volumes here and here, and these values are bigger. How did they get that big? This one's bigger because that value, this value, this value is greater than that value. Moles of A equals moles of B. A is false. Solution B must contain more moles of HCl? No, it's the other way around. Moles of A must be greater than moles of B. Right? So, as given, that's a false statement. If you have equal moles of HCl in both solutions, solution B must have a greater volume. All right. If we have equal moles, all right, how did we get equal moles? Well, if this is greater moles than that, then in order to get equal moles, we have to have less volume. Smaller volume of this will decrease the amount of the number of moles that you have. All right, so the number of moles of A should be less than the number of moles of B. Is that the statement? Solution B must have a greater volume. Oh, excuse me. If this is greater than that one, and we have, oh, we have equal moles, excuse me. We have equal moles. Then what does that imply? If we have equal moles, we have to have lesser volume here. That means greater volume of B. Is that what it says? Yes, greater volume of B. So L of B is greater than L of A. This is true. C, to obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. If you add volume to B, makes it less concentrated. It decreases the molarity, which keeps it even smaller than this one, right? So in order to have equal concentrations, you actually need to add volume to A and decrease its molarity to equal B, right? So as given, C is false. How about D? Adding more moles of HCl to both solutions will make them less concentrated. If you add more solute to each one, it'll make them both more concentrated, right? So D is also false. So A and B are the only true ones in this group. Why did we say? Oh, excuse me. B is the only true one. I don't know why I said A. A is false. B is true. And C and D are both false. All right. Now let's look at our solution in terms of ion concentration. For a 0.25 molar calcium chloride solution, remember what happens to ionic solids when they go into solution, and we're probably talking about aqueous solution here. What happens? The calcium chloride in aqueous solution actually breaks up into calcium ions and chloride ions, right? You have to have the same number on this side as you do on this side. 1 and 1, 2 and 2. All right, that's what happens. If you get a complete dissociation of calcium chloride in solution, then they will break up completely into these ions. Now, the 0.25 molar concentration here means 0.25 moles of that formula unit per liter, right? 0.25 moles of that formula unit. Well, the ratio here is 1 calcium here, 1 calcium there. So that means this side will also give you 0.25 moles of calcium ions per liter. But how many chloride ions will it give you? Well, for every one of these, you get 2 of those. So this is going to be 0.5 moles of chloride ions per liter. All right. Okay. We're going to compare solutions. And for this type of problem, I invoke Henry Ford, assembly line. Here's how you do it. And what I'm talking about assembly line is you do the same thing over and over again. Say I'm on the assembly line and my job is to put the left rear wheel on the vehicle. I do that all day long. Well, if a different vehicle comes along and I check my my instructions and it says this one gets a certain size wheel. Well, I put a different size wheel on that one, but it's still the left rear wheel. But I'm doing the same thing over and over again. I may change the size of the part to match. Well, that's what we're going to do here. We're going to take each one of these possibilities and calculate the number of ions produced in each one of these solutions, and then compare them. All right, so we have A, B, C, D, and E. No, just D. Just D. Okay, for A, we're starting off with 400 milliliters of 0.1 molar sodium chloride. If we want to calculate the number of ions, first we need to know how many formula units we have. And we can go back to the original formula. Molarity equals moles divided by volume. If we want to know the number of moles of ions, we have to have the number of moles of the compound. So we solve this equation for moles. Molarity times volume equals moles. All right, so that's where we're headed. Molarity times volume. The first one is 0.10 molar sodium chloride. The second one, oh, they're all 0.1 molar. Okay. This one is calcium chloride. And this one is iron 3 chloride. And this one is sucrose. Okay. Now, that's molarity. We want to multiply times volume to give us the number of moles of the compound. Now, why didn't I bother with this one? Because sucrose is not an ionic compound. It does not break up into ions. So we don't need to do that one. All right. The volume needs to be in liters. It's given to us in milliliters. So move the decimal place 3 to the left and you have liters. 0.400. Actually, there are 4 zeros. Liters. Right? Then we have 300 and 200. Okay, see what I mean, Henry Ford? I'm doing the same calculation over and over again. This gives us the moles of compound. All right, so let's go ahead and calculate that. All right, we could do a chain conversion, but in this case, let's do this one first. 0.1 times 0.4 is 0.04000. 0.1 times 0.3 is 0.03000. And this is 0.0200. This is moles of sodium chloride. This is moles of calcium chloride. And this is moles of iron 3 chloride. Okay. Now to convert to ions, we need a conversion factor. For each one, we'll have a different conversion factor. So for every one compound, how many ions do we produce? We produce for this one 3 ions. No, excuse me. My mistake. How many ions? 4 ions. For this one, 3. 2 plus 1 is 3 ions. And for this one, 2. All right? So 2 times 0.4 equals 0.08. I'm not going to give the extra zeros because we're comparing. We're just seeing which one has the greatest number. Okay? And this is 3 times 0.03, which is 0.09 ions. And this is 4 times 0.2, which is 0.080 ions. So that solution and that volume gives us the greatest number of ions. All right. This is problem-solving technique, right? We've looked at these before, and basically what we're doing is we're saying, what's the question? If you got to answer a question, you need to know what the question is. Question is, which one has the greatest number of ions? How do you get there? That's the question. So we got there by using this formula and solving it for a number of moles. And then using a conversion factor from moles of compound to moles of ions. That's how we solve this problem. Right? That's the point. The solution with the greatest number of ions is not necessarily the one which has the greatest volume, and is not necessarily the one with the greatest number of ions per formula. This one, that's not the greatest number of ions. This is not the greatest number of ions. This is. And we wouldn't know that unless we had calculated those values. All right, what's a standard solution? A standard solution is a solution for which the concentration is known very accurately. Now, why would we need a standard solution? Well, for one simple reason. We're going to use that standard solution to compare it to some other solution that is either not known accurately or is not known at all. And we're going to use a procedure, usually, not always, but usually by some form of what we call titration. You physically combine the solutions in such a way that you can determine the concentration of the unknown based upon the concentration of your standard solution. Oh, we got a video. Okay. See, I have to start it. Oh, come on. There we go.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, I'll be taking you through the appropriate technique and procedure for preparing a chemical solution. One of the most important abilities at all levels of chemistry is the preparing of a solution of a specific concentration. First, we'll define some of the terms used in this process. A solution is a homogeneous mixture of 2 or more chemicals. For the simplest solution, a smaller amount of one chemical, called the solute, is placed in a larger amount of a second chemical, known as the solvent. Today, we will be preparing a solution of sodium chloride, using a small amount of sodium chloride as our solute, added to a larger volume of water, our solvent. Before beginning any experiment, it's important to observe appropriate lab safety procedure and know the hazards of any chemicals you're working with. In any chemical reaction, it's important to keep track of the exact amount of reactants present, and for stoichiometric purposes, we use the term mole to define the amount of a substance. A mole is a counting term, similar to a dozen eggs, where 1 mole is equal to 6.022 times 10 to the 23rd things. As you can see, this is a really large number. The periodic table uses molar counting as a means of converting to a more experimental term of mass. For example, 1 mole of carbon atoms has a mass of 12.01 grams. In a compound such as sodium chloride, it's made up of 1 mole of sodium atoms with a mass of 22.98 grams per mole, along with 1 mole of chlorine atoms with a mass of 35.45 grams per mole, giving us a total of 58.43 grams per mole of sodium chloride. This means of using mass to determine the amount of a substance is useful for pure chemicals. But in the case of solutions, we now have a mixture of multiple different substances. Therefore, we express amount as a concentration. The most common unit for concentration in chemistry is molarity, abbreviated capital M, which indicates the number of moles of solute dissolved in a certain volume of the total solution. This gives molarity derived units of moles per liter. It is very important to note that this is a volume of solution, not the volume of solvent. Today, we will be preparing 500 milliliters of a 0.25 molar sodium chloride solution. Before beginning, it's important to map out your procedure for preparing this solution. Here, we'll look at the amount of sodium chloride we need in this solution. We know that we want to prepare a 0.25 molar solution, which means that there is 0.25 moles per liter of solution. We also know that we only want 500 milliliters of this solution, or a half liter. If we multiply these two terms together, we can see that we will need 0.125 moles of sodium chloride. From earlier, we can remember that there are 58.43 grams per mole of sodium chloride. We can determine that the exact mass that must be measured out is 7.304 grams of sodium chloride. In lab, obtain some sodium chloride in a clean lab scoop, and using a balance with some weighing paper, measure out as close to 7.304 grams as possible, marking down your exact mass. Note that if you go over the desired mass, it's never appropriate laboratory procedure to put the excess reagent back into the original container. Always use an additional container to collect the excess. Once you've measured out your solid and recorded the exact mass, transfer all of the solid to the appropriate sized volumetric flask. Volumetric flasks are made specifically for this purpose and should be used over other less accurate labware, such as beakers, Erlenmeyer flasks, or graduated cylinders. Here, we just transferred our solute to the 500 milliliter volumetric flask. If any solute remains on the weighing paper, use a spatula or a small amount of water to transfer the remaining salt. Next, add enough water so that the bulb area at the bottom of the flask is approximately half full. This will give you enough room to swirl the liquid, allowing the solute to completely dissolve. Again, it's critical that all of the solute is dissolved prior to filling to the appropriate volume, as different solutes may take up more volume in solution than their undissolved salts. Now that the sodium chloride is completely dissolved, we can fill the rest of the bulb area and some of the neck with water. You should now carefully and slowly add water, our solvent, as it begins to fill the neck. Once you approach the etched or printed line on the neck of the flask, you should add solvent dropwise, monitoring the location of the meniscus. Water, as a polar solvent, tends to cling to the glass walls of a flask. This phenomenon creates what is called a meniscus. The bottom of this curved meniscus should sit directly level with the line on the flask. At this point, there is exactly 500 milliliters of solution with an air of 0.2 milliliters. Different volume flasks have different air values. However, the air on a volumetric flask is much lower than any other type of glassware of similar volume. For example, the volume markings on a beaker or an Erlenmeyer flask are only accurate to plus or minus 5%, meaning if the meniscus were on the 500 milliliter line, it could be anywhere between 475 milliliters and 525 milliliters. On the other hand, using a volumetric flask, we know that the volume is exactly somewhere between 499.8 milliliters and 500.2 milliliters, meaning it's much more accurate. We now must determine the exact concentration of our solution by taking the mass that we measured out and dividing by formula mass for sodium chloride, 58.43 grams per mole, which gives us a total number of moles in our solution of 0.1253 moles. We can then take this number and divide by our volume of 0.5000 liters to give us a total exact concentration of this solution of 0.2501 molar sodium chloride. This value and the contents of the solution should be clearly labeled on the chosen storage container for laboratory safety protocol. You've now learned how to make a solution from a solid. Everything you need to do this demonstration in your lab is available from Carolina. We have experts who can assist you with any of your science demonstration needs. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
All right. There we go. When you're making a standard solution like this, I'll point out several things. One is we originally calculated the mass of the solute that was required. I think it was 2.5 grams. I believe, yeah, 2.5 grams. Or no, it wasn't. It was something else. Anyway, we calculated the amount of mass that was needed. But then when we actually weighed out that amount, remember that we've got individual grains of the compound, and we can't choose which grain is which very easily. So we may get a higher mass or a lower mass. But then we have the actual mass. That's the one that went into the calculation of the concentration. The actual mass, then converted to moles, then divided by liters equals molarity. Now, for this particular procedure, we had sodium chloride was the solute. So there was no particular hazard in putting the solute directly into the flask and then adding water. But there are some solutes that when we put them in solution, when we add water, they get very, very hot very quickly. And in those cases, they can get so hot as to boil the water. And if there's just a small amount of water when you first add it, then there might be enough heat to boil that water, evaporate that water, and it will spatter. And there's a hazard there. So for those types of chemicals, we add the solute to a smaller amount, actually a larger amount of solvent. That way the heat is absorbed by the solvent, and then we put that into the flask and dilute it. So that's one safety precaution that you may want to use. And examples of that are solid bases or concentrated acid solutions that we want to dilute. We have a rule of thumb. It's called do as you oughta. Add acid to water. In other words, don't add water to acid. Don't add water to concentrated acid, because all concentrated acids are, when they go into solution, are exothermic. They give off lots of heat. Sodium hydroxide is the same way. Potassium hydroxide, lithium hydroxide, any of the hydroxides will produce massive amounts of heat. So what you do is you put those into a larger amount of water in a separate container and get them into solution first, then add them to your volumetric flask and bring them to volume. Now, that's one precaution. That's the safety precaution. The other one is accuracy precaution. When we mix a solute with a solvent, it may become cold or it may become hot. And these volumetric flasks, this glassware, is calibrated to contain a given volume at a known temperature, usually 25 degrees. So if your solution gets cold when you mix it, it's going to shrink. And if you put a cold solution in your volumetric flask, right, and there's your marking right there. If you put a cold solution in there and bring it to volume, when it's cold, what's it going to do when it heats up to room temperature? It's going to expand. And then you'll end up with your solution is not to the volume. All right. So what you do is you mix the solution and just fill it up to about right here. And let the solution equilibrate to room temperature. Then remix it and fill it to the line. And then you want to put a cap on it or something to seal that off and mix it further. Make sure it's thoroughly mixed before you try to use it. Okay. Hot solutions are not quite the problem because if it gets hot and you fill it to the line right here, then when it gets cold, it's going to shrink, right? So if it gets hot and you fill it to the line, it's going to shrink. You let it come to room temperature, and then you can mix it and bring it to the volume. It's the cold solutions that give you the trouble. Okay. Those are two precautions: safety precaution, accuracy precaution. These are things that could go wrong, right? You could make an error in weighing, right? Or transferring. Remember our instructor there on the video cautioned us about transferring everything that was on the weighing paper into the flask, right? And usually, and especially if the material, the solid in this case, is hygroscopic, it will absorb water and stick to the paper. So what I always do is with the paper, or sometimes we use weighing modes. They're plastic containers like that. And I will hold those, and they're made so that you can squeeze them from the outside, and they make sort of a funnel. And you can squirt your extra solvent into that space and rinse everything into your flask. That's called quantitative transfer. That's a skill that you want to acquire and use continuously in these procedures. The other possibility is you don't let the solid go into solution completely before you dilute it to volume. You need to be sure that the solid is completely dissolved before you bring it to volume. And then, of course, you could, as you add your volume to the mark, you may miss the mark, too low, too high, right? If you don't remember that these devices are calibrated for the bottom of the meniscus in aqueous solutions, they're calibrated for the bottom of the meniscus. I've seen students come along and think that is an accurate volume at the top of the meniscus, and it's not. It needs to be the bottom of the meniscus, right? You could do it that way, or these volumetric glassware is scored all the way around. the dilution mark is etched in the glass all the way around, because if your eye is positioned up here, then you're looking down, and you may think that you've added volume in here, and you think it's on the line. Or if your eye's down here, you may be looking up, and you may see this one down here and you think it's on the line. Those things are scored all the way around so that you know when your eye is level. If you see a single line, then your eye is level. If you're too low or too high, you'll see the back line separated from the front. Right? So you want your eye level with the mark in order to visually verify that your dilution is exactly on target. We call this parallax error. Parallax is an off angle from a direct line of sight. I mentioned this one already. If the solution is exothermic, the heat of solution is exothermic or endothermic, then you can get a hot or a cold solution respectively for either one of those. And that will throw off your calculation, your dilution. There may be other possibilities. These are the major ones. All right. Now, let's say you've made your solution of known concentration, but you want a diluted version. In other words, a lower concentration of the solute. Well, all you have to do is add some solvent, and that will change the concentration to a lower value. But we went to all this trouble to make a standard solution of a known concentration, and we're just going to dump solvent into it. We want to know what is the concentration of the diluted version. Right? This is the process of dilution. It doesn't alter the number of moles of the solute present. It just changes their concentration. Right? This is an intensive property. And if we change either of the values, if we change either one of these, we change the molarity. If you increase this value, you decrease this value. If you increase that value, you increase this value. Or if you decrease this value, decrease that value. It's easier to change the volume. Let's put it that way. All right. So what we want to do is dilute a known amount of our accurately prepared stock solution. We call it a stock, to a working solution of a lesser concentration. All right. And in order to do that, we need to keep track of all our numbers and dimensions. And the whole process is based upon the concept that the moles of the stock solution that you take out are equal to the moles of the solution of the moles of the solute you put in to the diluted version. Let me draw you a picture. Let's say we have a solution here of 1 molar concentration. All right, got 1 mole per liter. And we want to put it into a volumetric flask. Right, of say, let's keep it simple, 1 liter. Now, this concentration is 1 molar. over here, we want this concentration to be 0.1 molar. All right? Well, so we're going to take out, rather than dilute that whole amount, we're going to take out part of it. But what we need to know is how many moles do we need in this solution? If we have 0.1 molar solution, then we have 1 liter of it. Right? Molarity equals moles divided by volume. We need to know what how many moles we need. So moles equals molarity times volume, and that is 0.1 molar times 1 liter is equal to 0.1 moles of solute. So we need 0.1 moles of solute out of here. Okay. Molarity equals that to that. So we need, how much volume do we need to take out so that we have 0.1 moles? So we put the volume over here, right, like that. Right, I just put the volume over there, put this over here, we can calculate volume. So this is 0.1 moles is what we need out of a 1 molar solution. That is, we need 0.1 liters of solution, or 100 milliliters. So if we take out 100 milliliters here, that means we've taken out 0.1 moles. Okay? And we're going to put 0.1 moles in this container. Right? And if we put 0.1 moles in 1 liter, we have 0.1 molar. All right, what makes this possible? What makes it possible is the number of moles you take out of here are equal to the number of moles you put in here. So what we're saying is the moles from the stock equal the moles in the working solution. Okay? That's what we're saying. Moles we took out of here equals moles we put in there. So this is going to be equal to molarity of the stock times the volume of the stock equals the molarity of the working solution times volume of the working solution. Or sometimes we write it M1 V1 equals M2 V2, or MC VC equals MD VD. Right? Molarity of the concentrated times the volume of the concentrated equals the molarity of the dilute times the volume of the. That's the formula that we're depending upon. Now, in order to use this formula properly, you need to be sure that you use the correct values in their right position. So if you're given a word problem and it says, what volume of a 1 molar solution do I need to put into a 1 liter volume to give me 0.1 molar of the diluted solution? Then what you need to do is set up a table. And extract from that problem that value, that value, that value. And that's the question. Then when you put your values in here, you put them in the right order and you get the right answer. If you don't do that, then you run the risk of putting your values in the wrong place and get the wrong answer. All right, now we're going to get, I think it's the same guy that's going to talk to us about dilution.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today I'll be taking you through the appropriate procedure and technique for diluting a solution. A common laboratory technique is preparing a more dilute solution from a concentrated stock solution. In this case, we are going to prepare a 0.250 liter solution of 0.01 molar. We know our stock solution has a concentration of 0.250 molar. The first thing we need to do is determine the exact number of moles in our dilute solution. We know our concentration needs to be 0.01 molar or 0.01 moles per liter. Since we know our number of moles per liter and we know the volume we need, we can calculate that we need exactly 0.0025 moles of sodium chloride. Knowing our stock solution contains 0.25 moles per liter, we can take the number of moles needed in our dilute solution and divide by the concentration of our stock solution to calculate the exact number of milliliters that must be transferred into our new solution. In this case, 0.01 liters of sodium chloride solution, or 10 milliliters. This is the stock solution of sodium chloride that we will be diluting. Make sure to pour the stock solution into another container before inserting the pipette into the solution. This is because you do not want to contaminate your stock solution. In this case, I'm using an Erlenmeyer flask. Notice that I have clearly labeled the flasks to adhere to proper laboratory safety protocol. To prepare our dilute solution, we will take a 10 milliliter aliquot of our stock solution using a 10 milliliter volumetric pipette. To use the pipette, place the pipette in the liquid to be collected. Squeeze the pipette bulb and allow the liquid to rise up the pipette. You should allow the liquid to pass the line marked on the pipette, but before the bulb. Remove the bulb and place your other thumb over the end, creating a seal, and slowly release just the corner of your thumb, allowing the liquid to exit so that the meniscus is directly on the line marked on the pipette. This takes some practice, and you may need to use the bulb to pull more liquid into the pipette again. Never pipette by mouth. Once you have the exact amount of liquid required in the pipette, hold your thumb firmly over the end and transfer the pipette to a new volumetric flask, in this case a clean 250 milliliter volumetric flask. Allow all of the liquid to flow out of the pipette. Do not use the bulb to force the liquid out, as pipettes are designed to deliver the exact amount of liquid, and there may be a small amount of liquid remaining at the end. Remove the pipette and follow the same procedure as before, filling the volumetric flask with solvent, again monitoring the meniscus until the exact volume is reached. You've now learned how to prepare a dilute solution from a stock solution. To see how to prepare a stock solution, you can view our solution preparation video at carolina.com/video. Everything you need to perform this technique in your lab is available from Carolina. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
There we go. Okay. So if we take the information that our instructor gave us, a concentrated solution is 0.25 molar, our diluted is 0.01 molar, and our final volume is 250 milliliters. And we want to find out that value right there. So the video, the instructor went through step by step, but there's actually a simpler way to do it. Just use the formula. Okay. If we have this information and we have this formula, we want to solve for this unknown. Here we go. Right? And now we have this value, we have that value, we have this value, and we can solve for that one. So all we have to do is put those values in. Let's see, the diluted is 0.01 molar. The volume of the diluted is 250 milliliters. And 0.250 molar. Okay, notice I did not change the volume here to liters. And the reason for that is this is a ratio. If we have the same units of measure here, notice they cancel. We have the same units of measure here, they cancel. So if you leave the volume in milliliters, your answer is going to come out in milliliters, which is more convenient. And then all we have to do is calculate 0.01 times 250 divided by 0.25, and that's 10 milliliters of the concentrated stock solution diluted to 250 milliliters will give us 0.01 molar working solution. Okay. Now the other mistake that our instructor made, he said that we don't want to contaminate the stock, so we pour some of the stock into a separate container, which is right. But when he put the pipette into that solution, drew it up, and then let the volume drop down to the meniscus on the volumetric pipette, those are all good techniques. But when he pulled the pipette out of the stock solution, what's on the outside of the pipette? You know, big globs of that solution hanging on the outside that you're going to add to your volumetric flask, and they're not accounted for from coming from the inside of the pipette. Those need to be removed. So what you do is one is you draw up the liquid, you know, past the mark, then remove your pipette. Great. You wipe the tip with a chem wipe to remove all that glob on the outside of the pipette. Then drop to the mark. That's where you allow the volume to drop to the mark. And now what are you going to have? It's very likely you'll have a little drop on the tip of the pipette. So you touch the tip to the inside of your container. Actually, to inside of the stock flask. That removes that from that extra value amount that's dripped from the outside. Now you're ready to deliver. Now deliver. Okay. That guarantees accuracy of your volumetric pipette. Okay. About out of time. I want to finish this discussion on dilution, and then we'll stop, and I'll pick it up again Thursday, part 2. But to finish the discussion, we've already covered this. It's in the video. And this is a challenge problem, which we should be able to knock out fairly quickly. Let's see. Let's just remove these because I have a feeling we're going to need those. A 0.5 molar solution of sodium chloride is in an open beaker sitting on the lab bench. Oh, no. All right. This is a qualitative thought problem. Which of the following would decrease the concentration of the salt solution? Right? You got this solution sitting out on your bench. That means the solvent is evaporating gradually, right? Water is evaporating. Sodium chloride won't evaporate. So how would you decrease the concentration of the salt? Add water to the solution? Yeah, water is the solvent. If you add solvent, you're going to decrease the concentration. Pour some of the solution down the sink? No. Concentration is an intensive property. So if you remove some of it, you've still got the same concentration in what remains. Add more sodium chloride? No, that will increase the concentration of the solute. Let the solution sit out on the open air? No, I just said the solvent is evaporating. If you decrease the solvent, you increase the concentration of your solute, right? At least two of the above would decrease? No, only one would decrease, and that is A. The rest would either no change or increase. And of course, E is false because you don't have two that are true. All right. Now we're going to use, what's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.8 molar sodium hydroxide? So extract from the problem. What's the concentrated concentration? 2.0 molar. What's your target diluted concentration? 0.8. Right? What's the final volume? What's the volume of your working solution? 150 milliliters. This is our unknown, right? So we're solving for this one again. BC equals MD BD over MC. Now that we have our values in the proper place, we can just plug them in, right? So we're going to have 0.8 molar times 150 milliliters divided by 2.00 molar. Now that's the thinking part. That's the hard part. That's the thinking part. The rest is number crunching. 0.8 times 150 divided by 2. And that is 60. You need 60 milliliters of the concentrated solution diluted to 150 milliliters will give you 0.8 molar solution. There it is. And I think, right, that's true. You don't have to change the units for volume because it's all a ratio. Only when you use this formula, separate and independent of anything else, in that case, you do need to put the correct volume units here, liters. Okay, we're going to stop here and pick it up on Thursday. Part 2, talking about stoichiometry, using solutions, right? I don't want to rush things. In fact, I'm out of time. So that's where we're going to pick it up next Thursday.